All right, so we're looking at, remember that when you actually look at simultaneous equations, like there's 1, 2, 3, 4, 5 situations that happen, all right? Now, when we talk about the first situation is when you actually have a unique solution. So a unique solution is when you have values for x, y, and z, okay? Now, when they say the geometry, I mean, like, this is the type of questions that you guys have been doing all this time. You know, when you did, what do you call it, like the pizza problem where you actually found what the regular, mini, and large sizes were. That's actually a unique solution because you got a value for x, you got a value for y, and you got a value for z. Now, the geometrical representation, it's like, you know, as you can see, it's like three planes that can intersect at one point. Now, if you're having problems drawing the shape, I think the best way to do it is, like, if you can think about it like this, you know, you've got a plane that's like, when I say a plane, because your equation has x, y, and z, because it has x, y, and z, it's a plane. But if it's just x and y, then it's a straight line, or it's a two-dimensional shape. But the moment you have x, y, and z, it's a three-dimensional shape. So in this case, you can imagine it almost like three faces of a cube. So you know how you got, so three planes, but they actually all meet at this point right there. Okay, and that point right there is to be known as, that's how what a unique solution is, because it has a unique value for x, y, and z. So that's your first kind of thing that you need to remember about. So now we go into inconsistent. So with inconsistency, like, solutions is that you've actually got three different types, okay? And I think this is the thing where you actually need to start looking at the numbers itself in your equations and not everything else. So the first situation we're going to be talking about is the parallel one. So with the parallel one, hang on, let me just move this. So with parallel one, now if you guys remember in when you had parallel lines look like this, right? Where you have two lines, well, that are not really meeting each other. Okay, so this is when we talk about parallel lines, this is what lines are going to look like. But with three equations, you have parallel planes. So imagine it like three sheets of paper put on top of each other, but they're not touching each other. Does that make sense? Mm-hmm. So that's what you call parallel planes. Now, if you're going to draw it, you could probably draw it something like that. I mean, it's the same three planes. It could be any size. The size doesn't really matter, but as long as they're not actually touching at all, the planes are not touching each other at all. All right. So that's the visual representation of it. So how do we find out if a plane is parallel or not? Is to actually look at your coefficients. All right. To look at the numbers of x, y, z, and the final number itself. Now I'm going to give you guys what do you call it? An example on straight lines, and then I'll show you an example on the 3D versions. All right. So when we have a look at two straight lines, two parallel lines, all right, what you might have is, like, you might have an equation of y equals to x plus 2, and the blue one could be like y equals x minus 2. This is for an example. All right. Now, if I rearrange these two equations, this one I'm going to get negative x plus y equals 2, and the blue line I'm going to get negative x plus y equals negative 2. Now, if you look at the coefficients, when I say the coefficients, I'm talking about these numbers here. So that's the coefficients right there. All right. Can you see how the numbers are negative 1, positive 1, negative 1, and positive 1? That's how I know that these two are parallel lines. If the coefficients are the same, but the constant is like completely different number. Okay. So if that's the case, we can look at the 3D version. So with the 3D version, what happens is, I'm going to give you guys an example. So if I have something like x plus y plus z equals 10, and then 2x plus 2y plus 2z equals 5, and then 5x plus 5y plus 5z equals 2, for example. So in this case, you can easily see that these are parallel lines. Now, if you're not sure whether they're parallel lines, what you can do is, remember how I showed you guys that little matrix that we can create, like this one here, and you just write the numbers, the numbers, and not with the letters. So I'll just write this as 1, 1, 1, 10, 2, 2, 2, 5, 5, 5, 5, and 2. And what you can see is that row 1, when row 1 is multiplied by 2, you actually get row 2. And if you take row 1 and actually multiply it by 5, you get row 3. But the problem is the numbers, the constants are not getting multiplied. They're different. Yeah? And that's how you know that if this situation happens, this is going to be 3 parallel planes. Okay? So an example could be, let me show you guys an example in this. So if I say, I'm going to write this down. So let's say, example, we've got x plus y plus 2z equals 4, and you've got 3x plus 3y plus 6z equals 10, and then I say something like, wait, let's change the color on this so you guys can see it. If I put it as px plus qy plus 8z equals 1, and if I ask you what should p and q be so that this is three parallel planes, what value would you guys put?
4.
Why 4?
Because in this row it's multiplied by 3. Like if you look at this one and you times it by 3, you get row this one.
Yep.
So you'd find out what you get to times it by.
You guys see what she's trying to do there?
Yeah.
Because if you look at this number here, so you've taken row 1 and you multiplied it by 2.
3.
Sorry, 3. But the number doesn't really matter, the constant doesn't matter.
Yeah.
But in the third row, if I want this to be all parallel planes, I've taken 2, multiplied it by 4 to get to 8, which means I got to take 1 and I've got to multiply it by 2, which means q should equal 2. And
4.
oh yeah, sorry, thank you. Glad somebody's awake. So that's 4. And what is this one gonna be?
4 also.
4 also. Okay. So this is the situation when you have all 3 of them are actually parallel. Is that right? So it's always looking at the coefficients and actually try and find them as a combination of row 1 or row 2 or something like that multiplied by a number. Okay? Any questions so far on that? Okay. Okay. So now what we've had a look at is like we've had a look at 3 parallel planes, right? So another situation that could happen, so I think the first one we had a look at was inconsistent but parallel lines. Well, parallel planes, all 3 of them being parallel planes. But this, well, in your piece of paper, it's the third situation. But we have a set of parallel planes. So 2 parallel planes. So with 2 parallel planes, you know how we had in the previous example that we had a look at, we said we know that these 2 here were the parallel planes, like this one and this one. So then you can say, if you want the situation where you only want 2 parallel lines, you can actually say P and Q cannot equal 4, but it can be any other number. If it's any other number, then it won't be the third parallel plane. So you've only got two parallel planes, and then the third one could be like this, where it could intersect like this or something along that lines. Okay, that's pretty straightforward, isn't it? Because once you understand the three parallel planes, it's because you've got two equations that are the same, but the third one has to be some other number apart from 4 and 4. So if I was to write the same equation here, so say if I put x plus y plus 2z equals 4, 3x plus 3y plus 6z equals 10, and if I say px plus qy plus 8z equals 1, now if I say p equals 4 and q equals 4, then it becomes three parallel planes. But if p and q are different numbers, so if p and q is not equal to 4, then what happens is you have two parallel planes. Does that make sense, guys?
Yeah.
So that means if you're going to draw this as a shape, it might look like this, where you have one plane like that. You could have another one that's like, so they're both parallel to each other, but then your third one could either, I don't know, it can do anything. You don't know what it does because it's an inconsistent solution. So it could look something like this, for all I know. You know, it doesn't, it could meet once, it could meet twice, we don't know. Okay, so that's that second parallel, two parallel plane situation that could happen. So again, it's all about, if you're unsure, break the numbers down into that little grid formation, all right? Like the little matrix, and then you can actually see what the numbers are doing. Don't worry about the x, y's, and z's. Just look at the matrices. All right. So guys, so far you've actually learned three things, right? We've done unique solution. That's when you have an answer and they all meet at a point. Mm-hmm. The second type of one is you've got three parallel planes, or you've got two parallel planes. Now I'm going to show you the last one, which is the dependent, and which is the other one, which is the parallel to the intersection of other two planes. But they all, if the way I kind of teach this is that you've got this situation that happens. You solve it, you got a unique solution. From there, you can either make the things parallel, or you can do the other version, which is either dependent or inconsistent. With parallel, you've got all three planes that are parallel, or two planes. Okay. Now you guys got to remember the pictures that they come associated with, because when you're actually drawing it or describing it, you can just show a picture and just describe it by saying, okay, so this is when you have two parallel planes, and then one of them could be intersecting or not. So let's go to the third situation, which is I'm actually going to do equations are dependent first, and then I'll come back to the other one, the final one. All right. So this is the third situation before I come to the inconsistent one. And I know it's going a bit all over the place, but you guys will see the pattern at the end of the day. So this is situation number 3, when equations are dependent. Now with equations if the equations are dependent, you actually have infinite number of solutions. All right, this is the important part. Infinite solutions, and I'll show you guys why. Let's see, I'm gonna write this equation. We have, so how do you know if equations are dependent? For equations are dependent, all it is that if you take one equation, so equation 1 for example, or any, like, how do I put this? You can take any equation, and if you add them up, if you get the third equation, then this is what happens. So it could be like equation 1 plus 3 equals equation 2. If that's the case, then you have infinite number of solutions. You might also have it something like 3 times equation 1 plus 2 times equation 2 equals equation 3. As long as they equal, the moment any combination of equation 1 and 2, if you add them up and if you get the third equation, then they're dependent. Okay? Now here's the thing. If it doesn't equal the third one, then it's the other example, which I'll talk a little bit later on, which is the last, this triangle, the triangular prism here. Okay, so let's have a look. So give you an example. We'll put in some equations. X plus 2y plus z equals 5, and then we'll have 3x plus y minus 3z equals 10. And then the last one could be something like 4x plus 3y minus 2z equals 15. So right now, you guys having a look, you can see 3 equations, right? So if you're on, like I said, anytime, just draw that little matrix. Okay. So if I draw this as a matrix, I've got 1, 2, 1, and 5. I've got 3, 1, minus 3, and 10. And I have 4, 3, minus 2, and 15. So can you guys see something happening here?
Yep.
What do you see, Brody?
1 plus 2 equals 3.
Yeah, so this one I gave you a nice and simple equation so that you guys can actually see this, right? So if you see this, equation 1 plus equation 2, just looking at the numbers, you can see that they actually add up to each. And they have to, every one of them have to add up. All right? Every number has to add up. So you can't just go like, oh, I'm just going to do 3 and then not worry about the number. Okay, if every number adds up, then you have a situation where the equations are dependent. Now, in terms of a diagram, what it actually looks like is, so you've got a paper. All right, so I'm going to put my little paper here. And then you have a second paper that could actually kind of cut through it in the middle. All right, and then you have a third paper. Now, this is the one I always struggle to draw it, but let's try my best here. So something like this. I need a different color. Hold on. So probably I should have really drawn this a bit up by the looks of it, the black one. What I'm trying to show you guys is like, yeah, somewhere there where all 3 sheets meet. So if you can imagine it, it's like oh, actually a better way to show this would be this actually. So you know how you take a book? You open up a book.
Oh, the spine.
Sorry?
The spine.
Yeah, like it's the binding part of the book. Because you can actually have 3 planes. If I open this right here, so look at this. That's 3 planes. They all meet at a single line, which means you've got, can you hold this now? You've actually got solutions, infinite number of solutions from here to here. So that's another way of kind of thinking it like this. So you have a, what do you call it? You have like a page that's opening up like this, and then you probably have something like that, and then that's like a simpler idea behind it. But I mean, it could be any one of these combinations, but that's just to get you guys into the idea that it actually meets, it's where that page binder is, that's where that line is. And as you can see, it's not a point anymore, it's a line, and anytime you have a line, you have infinite number of solutions. Okay, so let's do an example, and then let's see if you guys get the idea of this. So let's say I'm gonna make this 3x plus 2y. Let me pause this so I don't have to watch it all. Okay, just remember I actually made this question up on the spot, so have a look at the values. You've got 3x plus 2y plus z equals 5, and then 2x plus y plus z equals 3. Px plus 4y plus qz equals 11. Now my question is, what values should you put p and q so you have infinite number of solutions?
Wow. Can we times it?
Yeah, of course.
Wow, so
It's a linear combination.
Times it by 2. Times
Yeah.
it by
Oh,
2.
no, don't tell us.
Oh, jeez. I thought you could say.
I already knew.
Sorry, man.
Yeah. Oh, sorry, baby.
We nearly done with the p and q values.
Yeah.
Did you get it?
Yeah.
You can't remember how to do it.
No, I was
Then?
just wondering how he got it so fast.
Who, him?
Yeah.
Oh.
You probably just looked at the numbers. Did you do a grid?
No.
You just looked at the numbers, right? What'd you get? Wow.
7x 5 equals
Okay. While you guys are doing that, I'm going to write the numbers down. 3, 2, 1, 5, 2, 1, 1, 3.
Huh? I got a
Okay, I got it.
back.
So, yeah, what'd you guys get?
7 and 3.
P is 7 and Q is 3.
Yeah.
So how'd you guys get that?
Just times the second equation by 2.
Okay, second equation by 2. But how did you know it was 2?
Just,
The Y.
yeah.
Yeah, through that.
Oh, no, I looked at the last
I looked
one.
at the last numbers,
Yeah.
the end numbers.
Yeah. So now you got to make sure it works for both the last fourth column and the second column.
So on this one, we have to look at the constant as well.
Yeah, because if the constant doesn't equal, then
it's
it becomes the next situation that I'm going to talk to you about. All right. So that's why it's really important to figure it out. Now, sometimes the numbers is not as easy as this. Okay. Sometimes when you look at this, going, right now you guys looked at the last numbers and you just got it straight away. But I'm going to give you another example, and I'm going to get you guys to do that. But that one I actually need to go away, and I need some time to actually write that question down because I want to give you a tricky one. Okay, so this one you guys got P and Q because you saw that equation 1 plus 2 times equation 2. Am I correct? Okay. So when you do that, so you've got 5 times 5 plus 3 times 2, which was 6, so it's 11, so it's fine. 2 plus 1 times 2 is 4, so it's fine. So then your P would have been 3 plus 2 times 2, which is 7. And then in this case, 1 plus 2, which is 3. Is that right? So 7 and 3. So in this case, you basically say, okay, P and Q has to be 7 and 3 if you want to have infinite solutions. Okay? But if you change P and Q to any other number, I think you might actually find unique solution. Okay? So another thing that you guys could do is, in your graphics calculator, if you get a question like this, is put these numbers. And if you get a solution, then you know you've done something wrong. Because for you to answer a question like this, if you have infinite solutions or no solutions, then your calculator should show a math error or something like that. Okay, that's another way to check whether you're putting the right answer. You get what I'm trying to say, right? So, okay. So the next one, I'm going to give you guys slightly a challenging question. So let me just write it up. All right, guys. So this is the
highest person in the company.
next question for you guys. I'll pause this so that you guys can actually have a bit of time to think about it. Okay, how long was it? Did I give you guys? About 5 minutes? Okay, you guys got 5 minutes. I think Noel's the only one that came with the answer, right? But he guessed in checks, so we're not really going to count that. Okay, so the way to do this is first, as I said, try and get the numbers out. So you've got 2, 3, minus 1, 7. And then you've got 1, minus 1, 2, negative 4. Then you've got 8.
It's plus 1. It's negative 4.
Yeah, what happened?
What?
Did you guys copy it wrong?
Yeah.
Ouch.
No, I got the negative 4. Okay.
Okay, look. So right now, this might seem a little bit weird, but I think it'll make sense to you guys. So we know that we're multiplying row 1 by some number, right? I'm going to call it this number as A, for example. Okay? And I know I'm multiplying row number 2 by some number, I don't know what it is, called B. And the resulting answer should be row 3. Am I correct?
Yes.
So we're all happy with that, right? So now, this is the part, it might be a bit of a mind blow for you guys, but have a look anyway. So what I can say is, so I know that if I go 2 times A plus 1 times b would equal 8. Would you guys agree with that?
Yes.
So I'm going to write that down, okay? So I've got 2a plus 1b equals 8. Now I can do the same for the last column here. So I can do 7a multiplied by plus negative 4b should equal 13. So I can write that as 7a plus, oh, not plus, minus, isn't it? So I can write
Won't
this.
we have to add it?
Sorry?
7a plus negative 4b.
Yep, so positive and negative. Still going to be negative, right? So that's going to be negative 4b equals 13. Now what type of equations do you see here?
Simultaneous.
Simultaneous. So go into your calculator for simultaneous and put it into two, instead of two unknowns right now. So you should put 2, 1, 8. Well, 3 and 2. So no, you had the 3 and 2, right? So that's how you know that the value for a is equal to 3. So a is equal to 3 and b is equal to 2, which means now you can find the value for p, because you can just go 3 times 3 minus 1 times 2 equals the value for p. And then, so I'm doing it here. So 3 times 3, negative 1 times 3, and then negative 1 times 2 here, and 2 times 2. And that should give me the values for P and Q. Make sense? So I believe my final answer would be, I've got 3 times 3 minus 1 times 2 equals P. And then my Q value is negative 1 times 3 plus 2 times 2, which equals to Q. So in the end, P is equal to 9 minus 2, which is 7. And Q is equal to negative 3 plus 4, which is 1. You get 7 and 1?
Q is minus.
Q is minus 1.
Right.
That is not right.
You have a minus 1.
How? Isn't it 2 times 2?
The first one is a negative. You know how this becomes a negative 3, right? And this becomes a 2.
Which one? Yeah, but it's 2 times 2, bro.
No.
You didn't double it. You didn't double it.
No.
That's the difference between an excellence and a merit, right there.
Oh man.
It's alright. I think we'll give you as a resubmit, and if you don't pick it, then tough luck. So you guys understand how to get the P and Q values for dependent?
Yeah.
Now, here's the secret. For the final situation, which was when each plane is parallel to the intersection of the other two planes, all it is that you do the same thing as you did for the infinite solutions, but except the constant will not be equal. So in other words, you're right, Brody? Or?
Yeah.
So in other words, the last thing that I was having a look at, we just had a look at equation 1 plus equation 2 equals equation 3. So when you do that, you have infinite number of solutions. But if you do equation 1 and equation 2, and it equals the x and y things, but it doesn't equal the third one, I'll show you what I mean by it. So this is our second situation, when each plane parallel to intersection of other planes. So let's have a look. So what I mean by is, you know how in the previous example we had something like x plus 2y plus 3z equals 1, and then 2x plus 4y minus z equals 7, 3x plus 6y plus 2z equals 2. So if you guys have a look at this, equation 1 and 2, if you add them up, the x values add up correctly, the y values add up correctly, the z values add up correctly, but when you look at the constants, they don't actually add up correctly. So if this is the case, Because if this final number was not 2, but let's say it was 8, then you have infinite solutions. But because you have 2, it actually becomes this situation here when the plane is parallel to the intersection of the other two planes. So in other words, the diagram for this, it's going to look like this. It's just simply a triangular prism. Oh. Damn it. Where is it? There you go. So it looks like that. So it's 3 planes meeting like at a triangular prism. Okay, so sometimes you can get asked questions like, what can P and Q be, so that you have this kind of situation happening, inconsistent solutions. Now remember, when the question actually asks you, now where's that last question that we did? Can I have a look at the last question on the page today?
Yeah.
Did you write it down?
Yeah.
So it said, find P and Q so that the system is inconsistent and give a geometrical interpretation. So with inconsistent solutions, you've actually got how many situations altogether? 3.
3.
Yeah, because you have the parallel planes,
Yeah.
then you have the 2 parallel planes, and then you have this triangular prism one. But if they tell you find infinite solutions, you can only find one lot of P and Q. Yeah, because that'll give you infinite solutions. Do you want me to give you an example on this so that we can give it a go?
Yeah.
Okay, so here's a question. You guys got to find P and Q so that each plane is parallel to the intersection of the other 2 planes. So it's like the previous one we did. Good thing. Basically, can you guys give me a situation where there's values for P and Q where there's infinite solutions, and then values for P and Q such that you get the situation here where it's parallel to the intersection of other 2 planes?
So we.
Yeah, so can you give me
2
2 situations, or 2 values for P and Q so that 2 different situations happen? So guys, we're just looking at the coefficients at the moment to figure out the values for A and B. So we've got, I'm just going to write down the numbers in the grid. So I've got 2, 3, 1, 1, minus 3, 1, 4, 5, and I've got P, 9.
Okay, that looks better.
Better?
Yeah.
What'd you get for your values?
4 and negative 3.
Good, that sounds more like it. Okay, so I've got row 1 times A, row 2 times B, right? And I'm only looking, Rochelle, I'm only looking at the numbers. I'm not looking at P and Q. I'm only looking with the 3 ones with 3 numbers in it.
Yeah.
So which means I've got 3A plus 1B equals 9. And the other one is the third column when I have 1A
I like every time I look at you, you're
plus 4B equals minus 8. Is that right?
Yeah.
Okay, so you guys got A and B, right? What'd you guys get for A and B?
A was 4.
It was
minus
4
3,
B.
yeah.
Negative 3. Okay, now this is what I want to show you guys. The difference between this question in terms of what I meant by for infinite solutions and for the other the other one where it's parallel to the intersection of the 2 planes. Now, I'm going to solve P and Q first for infinite solutions. All right? For infinite solutions, equation 1 must add up to, equation 1 and 2 should add up to 3, right? So that's for infinite solutions. So is that okay, Rochelle? So if that's the case, then my p-value is going to be 2 times a plus negative 3b should equal p. In this case, I'm going to get 2 times 4 plus negative 3 times negative 3 equals p. So what do you guys get? 8 plus 9, 17? All right, so p-value should equal 17. Now, as for Q, I've got 1A plus 5B equals Q. So I've got 1 times 4 plus 5 times negative 3 equals Q. So what's Q equal to?
Negative 11.
Negative 11. Okay. Now here's the magic part. Brody, you need to listen to this one. So once you got P and Q, right? Did you get P and Q?
Yeah.
We're working on it. Okay, so P and Q is solved. So remember I asked you for 2 things that could happen. If q equals negative 11, then you're going to get infinite solutions, because equation 1 times 4 minus equation 2 times 3 equals equation 3. So this is the case. If p equals 17 and q equals negative 11, you're going to have infinite solutions. But if you have p equals 17 and q is any other number except negative 11, then you're going to get that other situation.
You get this one.
Yeah, the one of the triangle. Because remember we said that in the triangle, the triangular prism that we talked about, the x, y, z's will add up, but the constants won't actually add up. So in this case, you can actually say if q is not negative 11 and if q is any other number apart from negative 11, then you're going to get a situation where the plane is parallel to the intersection of other two planes, or it's going to look like that triangular prism. So basically, you've just done two situations in one by just solving that. Okay? So that's what I mean by. So you guys got to be aware of which one is which situation, and that's it.
Can we get more?
Yes, you have more in your actual textbook, but I've got some more as well that I'll give you guys. Okay, that's it. Okay, those for you on business trip. Good luck watching this, and if you have any questions, ask Rochelle. Actually, ask Noel. He knows.
No, that's
Okay, fine. Come and find me.
Ask Calvin.